Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at an introduction to Monte Carlo simulation. Monte Carlo simulation is actually a fairly broad topic. A lot of Monte Carlo simulation techniques that you might encounter over your career. Collectively, they're named after the world famous Monte Carlo casino in Monaco, where an understanding of the random nature of things can really pay off quite big. We're going to have a fairly limited discussion of Monte Carlo simulation. What we're going to do is look at ways to describe the randomness of the outputs of relatively simple electrical systems that have a single random component that is well described by a common random variable. Okay, we're going to be using techniques that we learned in the last video lecture on the computer generation of random variables in particular. All right, so let's begin with a quick summary of what we did in the last lecture. This will be a summary of estimating PDFs of common random variables. Estimating PDFs for common random variables begins this way. First thing what we do is we find a transformation . Find a transformation that converts a random variable, uniform, on 0 to 1 into some other probability density function. Okay? In other words, we have to calculate this. All right, x will be uniform on 0 to 1. Y is any other random variable. All right, and the transformation function that will convert a random variable x uniform on 0 to 1 into random variable y is the inverse cumulative distribution function for y evaluated at x. All right, so the next step is we generate n data points in my uniform random variable x using that function in MATLAB, the rand function in MATLAB. All right, we apply the transformation to x. We apply the transformation to the x data points to get n points in y. We then use MATLAB to create a histogram for the y data points. All right, and there's two ways we can do that. We can either start by picking the bin centers and the bin spacing, or we can just simply tell MATLAB the number of bins that we would like. Okay? After we create the histogram, we can estimate the probability density function h will be represent my histogram, ./n times delta y. H is my histogram vector, HIS. Histogram vector, I'll have m points in H. I'll have m points in H, each centered at a bin. Delta y is my bin spacing. You can either specify that up front when you're calculating the histogram, or you can let MATLAB calculate it for you. All right. You can plot. You can plot the probability density function estimate if you wish. All right. We can calculate the mean values for y, the mean squared values for y, the normalized power. We can calculate the variance, standard deviation, etc. for y using techniques I gave you in the previous lecture. And unfortunately, you have to fiddle with the bin spacing and bin centers until my results are what I expect them to be. All right, so I fiddle with the bin width and the bin centers until PDF estimate is smooth. Okay? Hopefully you remember this from the last lecture. For Monte Carlo simulation, we're going to take this one additional step. Really, we're going to do one additional thing to all of this. Let me just sketch this out as a diagram. So for Monte Carlo simulation for us, we're going to do this. I'm going to start by assuming I begin with a random variable that's uniform on 0 to 1. Okay? I'm then going to convert x into some new random variable y. All right? And I'm going to apply that to some system. Okay? And that system is going to be described by some function. And I'm going to have an output, let's call this z, which will be a function of input y. All right? All right? Does that make sense? So what we're going to do is we're going to have a circuit, a system of some sort, which has an output value z. So z here will be some output. And y will be an input or a parameter that z depends upon. All right. So for our discussion, we're going to limit our output for us. Our output will depend on only one random parameter. And I should say it this way, we're going to look at a single output. Whatever our system is going to have a single output. single output, a single random parameter that affects Z. All right, I'm going to have a system that has a single output, and my single output is going to have, it may have multiple fixed parameters that it depends upon, but it's going to depend upon only one random parameter, single random parameter. And for us, we're going to assume that the random parameter behaves according to a well-known probability density function that we've already been talking about. All right, so my single random parameter is going to behave according to a well-known probability density function that we've already been talking about. All right, so what I'm going to do ultimately in MATLAB is we'll generate a bunch of data points uniformly distributed on 0 to 1. I'll calculate some new parameter, maybe it's a resistor, maybe it's a capacitor value, using my first transformation of variables, and then I will run those data points into another equation that describes the behavior, output behavior of some system, and calculate yet another random variable Z. Remember, a function of a function is a function. A random variable is a function. X is a random variable, therefore it is a function. Y is a compound function. It's a function of random variable Z. Excuse me, it's a function of random variable X. Z then is a function of random variable Y. Z is a random variable. Z is a random variable. And so I can perform histogram analysis on my data points in Z. Just go GRAM analysis. I can perform histogram analysis on my data points in Z, normalize my histogram to get a PDF estimate for Z. Calculate mean squared, variance, standard deviation, etc. Plot the probability density function if I want. I will say at this point that even though we're going to assume that we have systems with single outputs that depend upon single random parameters, and my single random parameter, in our case, will depend upon will behave according to a well-known probability density function. The behavior, the statistical behavior of Z will almost always be something we don't expect. All right, keep that in mind. All right. First thing I'm going to do, before we get into looking at a simple electrical system and how to examine it through Monte Carlo simulation, I want to do a classic example in Monte Carlo simulation that all students in such a course should be familiar with. It's the Monte Carlo simulation of the value of pi. Monte Carlo simulation to estimate the value of pi. All right, it's a classic example Introduction to Monte Carlo Simulation. You're going to write me a program to do the steps that I'm about to describe for you. All right. So let me set up the geometry of the problem. So I've got a square. That's supposed to be a square. And I've got some inscribed circle. All right. The radius is r. We'll let this be the x direction, and we'll let that be the y direction. All right, so I've got a square with a maximum inscribed circle. A square with a maximum inscribed circle. The area of the square is just going to be 2r times 2r. That's 4r squared. All right, so my box is 2r tall and 2r wide. All right. Area of my circle is clearly pi r squared. The ratio of the areas it's the area of the circle divided by the area of the square. That's just pi over 4. And I'm going to set that equal to a capital R. Okay? Now, here's where Monte Carlo simulation comes in. I'm going to pretend that I throw darts at my square. We're going to pretend we throw darts at the square. We're going to assume that all of the darts hit somewhere in the square. All the darts hit. Okay? We're going to assume all the darts hit the square and that they are uniformly distributed in x and y. Okay? And oh, by the way, I should probably say this. I'm going to assume that the origin of my coordinate system is right there in the center of my circle. That'll be important in just a couple of minutes. All right? So I'm going to pretend that I throw a whole bunch of darts at the square, bunches of them. I'm going to assume that all the darts hit the square and that they are uniformly distributed in x and y. All right, then. The probability of landing in the circular area is P sub c, and P sub c equals the limit as n approaches infinity of n sub c divided by n. That's going to be the ratio r that we seek, and that is going to equal pi over 4. All right. N sub c equals the number of darts that hit the circle. N, capital N, is total number of darts thrown. Okay. So then, let's jump to the next page. Therefore, pi equals the limit as n approaches infinity for this problem of 4 NC divided by n. All right? That is what we'd like to simulate in some Monte Carlo simulation code. All right? So you're going to actually write the code for me, but I'm going to give you some hints. All right. First thing we want to do is we're going to generate a couple of random numbers. We'll let x equal rand 1 comma n. We'll let y equal rand 1 comma n. All right. So what I have there is when I run rand one time, I'm going to get a different set of values than when I run rand a second time. So x and y are not going to be equal to one another here. Okay. X and y are not going to be equal to one another, even though I have n data points in each of those vectors. All right. So these are going to be unique vectors, n points long, and uniform on the range 0 to 1. All right. And then I'm going to remember, I chose the origin of my problem at the center of my circle. So really what I'd like to have is data that's uniformly distributed from -1, way down here. This is x equals -1, that point right there. And this point up here is x equals +1. Down here I have y equals -1, and up here I have y equals +1. What I'd really be interested in doing is taking my vectors here, x and y, and instead of having them distributed on 0 to 1, I'd like to switch them to being uniformly distributed from -1 to +1. So, you might want to do this. X equals 2x minus 1, y equals 2y minus 1. This gives me uniformly distributed data on uniformly distributed values on -1 to 1. All right. When x equals 0, when the initial x equals 0, my new x equals -1. When my initial x equals +1, my new x equals +1 as well. Okay? Then what I might want to do is calculate r equals square root of x dot x squared plus y squared. This now I have n radius values, or let's call it radial impact points. Okay. And then I can do some simple MATLAB code. Let me jump to the next page. I can start off by setting n sub c equals 0. All right, I start n sub c is the number of darts that hit the circle. We'll start off with it 0, and we'll do something like this. For I equals 1 to, excuse me, I need a colon there, 1 to n, if r sub I is less than or equal to 1, n sub c equals n sub c plus 1, end. All right, and then pi equals 4 nc divided by n. That'll be my estimate. This is the estimate that we seek. Okay? That's it. That's pretty straightforward. You'll see this in just about every introductory discussion of Monte Carlo simulation. And so what you're going to do is you're going to write me a simple MATLAB program that will allow me, literally me, you're going to email me the program, and you're going to allow me to change n. Vary the number of darts that I throw. And then you're going to write a program that will calculate pi and plot out, or excuse me, print out the value of pi and give me a percent error from the true value of pi. So what you'll find is that the percent error in the estimate goes down as the number of darts that we throw go up. All right? So when you write this code, try it for 100. N equals 100. Capital N equals 100. Try it for 5,000. Try it for 50,000. Try it for 500,000, 1 million, 2 million. You'll find that it converges pretty quickly. Okay? All right. So, I said earlier on that we were going to look at the output of some system, a single output of some system that depended upon some single random component or value at the input. Let's look at that. Simple system behavior, simple system behavior to a single random parameter. All right, that's what we're going to look at next. We're going to look at a simple system behavior due to a single random parameter. In particular, what we're going to look at is a voltage divider. Okay, so this is my voltage divider. V sub I will be my input. It's a DC circuit. That's a battery symbol. This will be resistor R1. This will be resistor R2. Hopefully from some circuit analysis course, you know that V naught equals V sub I times R2 over R1 plus R2. That's simple voltage divider relationship. All right. So what we're going to do is we're going to assume that Vi and R2 are fixed, but that R1 has randomness associated with it. My resistor R1 has an uncertain resistor value. R1 is random. Okay? We'll assume that resistor R1 has a known PDF and it's going to be one of our common, well-known PDFs that we've been talking about. All right. So what we're going to do is we're going to start with a random number, a random variable that's uniform on 0 to 1. From that, we're going to calculate a bunch of resistor values. Using my transformation of random variables knowledge. And once we calculate a bunch of random resistor values, we're going to calculate a bunch of random output voltages. Using my voltage divider relationship. So what I'll do is first I'm going to calculate in random values on 0 to 1 for X, plug that into this relationship here, and get in random values for R1, plug that in over here in the denominator of my voltage divider relationship, put each one of those random values R1 into the denominator of my voltage divider relationship, and come up with N values of my output voltage, do normalized histogram analysis on V0, plot the probability density function, calculate mean, mean squared, variance, standard deviation, all that kind of stuff. All right? All right. All right, let's assume for our case, and this is just purely an assumption, let's assume R1 is Rayleigh distributed. Okay? This is purely for purposes of giving an interesting result for us to talk about in a few minutes. It's almost 100% likely that no resistor manufacturer produces resistors that are Rayleigh distributed. More than likely, they are uniformly distributed about the mean value. So if you go down to Radio Shack and you buy yourself a 1 kilo ohm resistor, it's probably a mean value of 1 kilo ohm plus or minus some uncertainty that's uniformly distributed around 1 kilo ohm. I'm just going to pretend that it's Rayleigh distributed to give us an unusual, interesting result for us to discuss later. All right? A Rayleigh probability density function looks like this. Oh, I'm sorry. I did the math wrong. This is exponential. I'm going to assume that it's exponentially distributed. I beg your pardon. Exponentially distributed. My math is actually, I actually did my math assuming an exponential random variable, not Rayleigh random variable. I beg your pardon. All right, so my probability density function for R1 looks like this. Alpha e to the minus alpha x Ux. Okay? We have in the past discovered that the cumulative distribution function for an exponential random variable looks like this: 1 minus e to the minus alpha r1 with a step function in there. We have to invert this, and I'm going to set that equal to x in order to invert it. And this is my transformation function. Okay, that's my transformation function. We've calculated this earlier. Alright, so if x here is uniformly distributed on 0 to 1, I will end up with values r sub 1 that are exponentially distributed. Alright, we've also found earlier that the mean value for exponentially distributed data is 1 over alpha, and we've also seen that the variance is 1 over alpha squared. Okay? All right. I am going to assume for this problem for now I'm going to assume that the mean value for R1 is 1 kilo ohm, and I'm going to assume that Vn equals 12 volts DC, and that R2 is a fixed value of 1 kilo ohm. That's 1,000 ohms, folks. Okay? Okay, does that make sense? So what I'm going to do is I'm going to calculate, I'm going to use RAND, my RAND function, to get a bunch of points in X. All right, this is X. All right. Use my RAND function in MATLAB to create a bunch of points that are uniform on 0 to 1, and that's my random variable X. I'm then going to use my transformation function. To calculate a bunch of points for resistance. R1 equals minus 1 over alpha, natural log of 1 minus X. All right, this is in values of resistor R1. And then what I'm going to do is my output voltage is Vn times R2 over R1 plus R2. I'm going to get in values for my output voltage. And then I'm going to do histogram analysis using the techniques I taught you in the previous lecture. All right? do normalized histogram analysis like we discussed in the previous lecture. All right. That's my result. Okay? This is, on the upper right-hand corner, the plot of the probability density function for my voltage divider output. Okay? The mean value of R1 is 1 kilo. And I need to correct that. My R1 values are exponentially distributed. I beg your pardon. R2 is fixed at 1,000 ohms. Input is fixed at 12 volts. I fiddled with the data. I fiddled with the output voltage data until it looked reasonably smooth, and when I was happy, I was using 100 bins distributed between 0 volts and 12 volts. I used 500,000 data points for X. X is rand 1 comma n. All right. All right, that's where I started, and I checked it, and my PDF does indeed have unit area. Okay, all right. You'll notice that my PDF drops off real hard at 12 volts. Remember, my circuit looks something like this. This is R1, this is R2, this is my output voltage, and this is my input voltage. All right. When R2 is 0, when R1 is 0, when R1 is 0, my output voltage is exactly 12 volts. As R1 gets larger and larger and larger and approaches infinity with that long exponential tail, the voltage smoothly approaches 0. Remember, my exponential probability density function looks something like this. All right? All right? That'll be R1, 0. So it's got a long tail that approaches, that moves out towards resistor values of infinity. So it approaches 0 smoothly. When R1 becomes infinity, all the voltage is dropped across R1. There is no output voltage. Because of the smooth transition of my probability density function for my resistor values, I get a smooth transition back down towards 0. So this represents R1 equal infinity. Okay, but there's an abrupt transition in the exponential PDF towards 0 resistance values. That's why I translate to an abrupt drop-off, abrupt end to my probability density function for my output voltage at 12 volts. Now, the interesting thing I found in using an exponential probability density function for my resistor value is that I found this to be my mean. I used the MATLAB code that I showed you in the previous video lecture to calculate the mean based on my probability density function estimate, and I got a mean output voltage of 7.16 volts or so. That is entirely unexpected. So assuming R1 is exponentially distributed, assuming R1 is exponentially distributed, we found that the mean output voltage was about 7.16 volts. But that is absolutely not the voltage, that's absolutely not the mean voltage we would expect by looking at the mean values of R1. All right? If we assume that R1 equals 1 kilo ohm, that is the mean value, that is, if we assume that the value for R1 is its mean value, then, and also assuming that Vn is 12 volts and R2 equals 1 kilo ohm as well, then V0 is 12 times 1,000 divided by 1,000 plus 1,000, which is 6 volts. All right. All right. So using Monte Carlo simulation techniques, I came up with a probability density function and a mean output voltage of 7.16 volts, and that is absolutely not something I would expect by calculating the output voltage based on the mean value of my random parameter. I also claim to you that the shape of that probability density function is not something I could ever anticipate. It doesn't behave according to any probability density function formula that I've given you so far this semester. It is indeed a true probability density function. It's got unit area, behaves just like we would expect it to behave, but it's not something we would expect. All right. So the bottom line from all of this is Monte Carlo simulation oftentimes gives us non-intuitive insight into the behavior of systems that have random variables or random components somewhere in the system description. So non-intuitive sometimes we can get some rather non-intuitive behavior that's predicted by doing Monte Carlo simulation. By the way, I will be sending you I'm going to send you another MATLAB file. It's called Monte Carlo voltage divider. .m. All right, take a look at that. That's the MATLAB code that I use to calculate this PDF, the mean and standard deviation values that I have shown up here in the figure. All right. Very often, the most complicated part, well, there's two complicated parts to Monte Carlo simulation as we've described it. One is to calculate the transformation function that converts uniformly distributed data into data distributed according to a probability density function that you would like. That's one major step. Most of that I've done for you now through the semester. And the other big step is to calculate the output as a function of whatever random component or parameter that we have to deal with. You'll be examining Monte Carlo simulation a bit more through homework. And for today, that's all I've got. As usual, if you have any questions, please contact me at your earliest convenience, and I will attempt to answer your questions as fully as possible. That's all for today. Bye-bye.